Good afternoon, everybody. Welcome to our Sunday afternoon space show program. I'm your host for the program, David Livingston. Thank you very much for coming in. We will be doing some screen sharing today with our guest, Dr. Andrew Fraknoi, on lots and lots of astronomy and science questions and topics. So hopefully you're set up to view the Zoom thing and not just see it in the background or something like that. And a couple of very quick announcements. I will be at UCLA next week, so there will be no space show programs, but our next show should come in the Tuesday. I am back in town and check the schedule, everyone, to see who will be showing up and what the topic will be. That is Tuesday, March 10th. So I will be in contact with people. If you have a reason to email me, please do so. drspace@thespaceshow.com. And also remember, we are a nonprofit 501c3 listener supported, viewer supported program. So if you like us, please go to thespaceshow.com and there's a PayPal button on the upper right side. That's probably the easiest way to support us. And then if you're using Substack, Substack has its own way to support people. So please join and do that. And happy to field any questions you might have at, again, drspace@thespaceshow.com. Our returning guest today, Dr. Andrew Fraknoi, is a professor of astronomy at the Fromm Institute at the University of San Francisco and the National Ocean Online Project at Northwestern. Many of you probably know his voice and have heard him do astronomy and star reports for decades, having been in the Bay Area for 55 years. My sons grew up listening to his reports on the radio, as I have, and it's really fun and very enjoyable to meet him via Zoom and to talk to him on the space show. He has a full bio up on our website, so we want to maximize our time with him. So I urge you to read it because there's a lot more to his background. There's a really cool online free astronomy textbook and a lot more. But our guest reached out to me and told me there's a big total lunar eclipse in a couple of days and we should cover that. So welcome back, and can we see the total lunar eclipse in the western part of the country where you and I are?
Yes, indeed. Well, first of all, thank you for having me back. It's good to see you again. And yes, I there is going to be a total eclipse of the moon, and there's good news and bad news. The good news is that the total eclipse of the moon is very democratic. It's easy to see. You don't need special equipment. Eclipses of the moon last a long time. They're not like eclipses of the sun where they're over in 2 minutes. And so that's all great. The bad news is it happens in the middle of the night for every time zone in the United States. So you either have to get up really early or you have to get up in the middle of the night, depending on your time zone. And it's not a convenient time for a work day when people who are not retired need to go to work or school. So the sky is not always cooperative in terms of human schedules. But you asked about the West Coast. Here on the West Coast, the partial phase of the eclipse, where the Earth's shadow slowly starts to move across the full moon, that begins at 1:50 a.m., so roughly 2 a.m. The total eclipse, where the moon is completely covered by the Earth's shadow, and it gets this eerie red glow because the Earth's atmosphere bends red light better. And so the red light of the sun is still bent through the Earth's atmosphere. So the moon gets this eerie red glow around 3:05 a.m. And the total eclipse lasts for about an hour until 4:03 a.m., all West Coast time now. And then the partial eclipse is finally over. The shadow of the Earth moves off the sun at 5:17 a.m. So that's the time schedule on the West Coast.
Why is it being so uncooperative and showing up in the middle of the night?
It's a random. When eclipses happen is a random product of the geometry of how the sun, the moon, and the earth line up in their orbits. And so we can predict to the minute when it's going to happen, but we have no control over the schedule.
So I guess we can see it probably recorded online when we wake up at a reasonable time for
Well,
those of us.
that's right. And I'm sure the media will cover it, although there's a lot going on right now in the media. Um, but it's the kind of thing which generally happens pretty often. Eclipses of the moon are seen over half the Earth. So any part of the Earth, gets to see a total eclipse of the moon pretty regularly. But it just so happens that North America won't see another one until 2029. So if you miss this one, you have to wait 3 years before you get to see another one. So that's why some people are getting up in the middle of the night and taking a look at the
You have a
eclipses.
great chart for that you can show us, right?
Yeah, so I put together a little sheet that explains what's happening and gives the times for each time zone. And it's available at bit.ly /2026 eclipse, all one word. bit.ly /2026 eclipse. And I'll share the screen and show you what this looks like. There it is. It's a booklet that explains what's happening and then gives the times for each time zone. It's a little bit easier for the Eastern time zone. If you get up, you'll see the total eclipse happening starting at dawn. But by the time the total eclipse is over, the moon will have set in the Eastern time zone. So you pay a price for that. And I talk a little bit about what's visible, about the safety of watching. Um, and my favorite part about these eclipses is what you can tell your kids or grandkids, because this is really kind of fun. If you watch a total eclipse for a long time, for the whole period, or at least a good part of the period that the shadow of the Earth moon moves across the full moon, you see that the shadow of the Earth is round. And the ancient Greeks, thousands of years ago, began to note this. And they watched eclipse after eclipse after eclipse, looking at the shadow of the earth on the full moon. And the shadow of the earth was always round. And they began to think, well, what's the shape that always makes a round shadow? A round ball. And that was the beginning of our concluding that we live on a round earth. And as I say, this happened thousands of years ago from watching these total eclipses of the moon. So
How,
that's the sheet that you can get free on the web.
how could they tell it was round? I mean, what was the mechanism or the clues? Because they didn't have a telescope. So
Right, and you don't need a telescope. That's the thank you for bringing that up. So often when we astronomers get all excited about something in the sky, turns out you really need a good telescope to see it. And most people feel like, well, I don't have a telescope or I don't have a good enough telescope. This is for the 1%. But this eclipse doesn't require a telescope. The full moon is something all of us can see in the sky. And this is just the full moon getting a shadow and then turning blood red. So it's easy to see without a telescope. If you happen to have a pair of binoculars and you bring them out, you can see an enlarged picture, but you don't need it. So this is an astronomical phenomenon for the 99%, not for the 1%.
and they can tell it's creating something round because of
Yeah,
the
so you
shadow
see
on the moon.
the photograph on the screen. This is a photo that they took, that a NASA astronomer took, and you can see that the shadow of the Earth, that's the dark part. That at the beginning, this was a full moon, and the shadow of the Earth is round, and then when the shadow comes off the eclipsed moon, again the shadow is round. And seeing a shadow eclipse after eclipse being round gave them the notion that we live on a round planet.
Interesting. Um,
All right.
do they could they predict accurately when the next eclipse would be?
No, no. In those days, we were just beginning to develop the geometry and the mathematics to predict eclipses, but but indeed they were common enough, and they were seen on half the Earth each time they happened. So the ancient Greeks encountered eclipses of the moon much more frequently than eclipses of the sun.
You mentioned safety. What is the safety involved in viewing a lunar eclipse? Because it's not like the sun.
That's right. So this is thank you for bringing that up. So many people hear the word eclipse and they worry because they've learned from big news stories about eclipses of the sun that the sun is dangerous to look at and you need to shield your eyes. But we all look at the full moon without any problem. The full moon in the sky is something we've all enjoyed and love songs have been written about. And so the full moon is perfectly safe. And in an eclipse of the moon, the full moon only gets darker. So eclipses of the moon are perfectly safe to look at. You don't need special glasses. You don't need to keep the kids indoors. It's fine for everyone to go out and take a look at it.
Um, when's the next? Are they're geographically set up so that another one might appear, but we wouldn't see it in on the West Coast, correct?
That's right.
Same thing
That's right.
similar to the
So,
sun.
so the next one that we're going to be able to see is not till 2029. Um,
So if you're an active astronomer, do you find more value in wanting to observe and photo and deal with a lunar eclipse or a total eclipse of the sun?
great question. Yes, the eclipses of the sun are far more important for modern astronomy. The eclipses of the moon are more a beautiful sight for the public, but eclipses of the sun allow us to monitor the atmosphere of the sun. In an eclipse of the sun, the moon gets in front of the sun as seen from Earth. And I don't know if our viewers and listeners know this, but this is a remarkable coincidence. It just so happens that as seen from our planet, the size of our moon in the sky and the size of our sun in the sky happen to be exactly the same. We've actually calculated to see if this coincidence would work on any of the other planets. Mars has two moons, Jupiter has countless moons, and we've done the calculations and no, this coincidence is only true on Earth. And it wasn't even true on Earth all the time in the past. In the past, the moon was closer to the Earth, so it more than covered the sun. And in the future, millions of years, the moon is moving slowly away from us. But right now, at this particular moment, when you're listening to the space show, there's this coincidence that the sun and the moon in the sky are the same size. And I bring that all up because if that's true, then during an eclipse of the sun, the moon exactly covers the disk of the sun. And what we find is that the main disk of the sun is not the whole story. Outside that disk, there is a much thinner atmosphere around the sun, which we normally don't get to see when the bright sun is shining. But during the eclipse, where the moon has the courtesy to exactly cover the sun, then the faint atmosphere comes out. That atmosphere was discovered during an eclipse of the sun, and each eclipse still gives us the opportunity to study that atmosphere of the sun in exquisite detail.
I know Marshall has a question, but first, in terms of mythology and legend, are there any great ones around lunar eclipses like there are with solar eclipses?
Well, each culture has stories about the moon, and some of those stories do, in fact, involve the moon disappearing and coming back. But this is not a particularly rich source of legends, the total eclipse of the moon. It depends again on the culture. There are many cultural stories, and I'm not very familiar with all the different cultural stories of the sky.
Marshall, you have a question?
Yeah. My fun question comes from a lecture like 40 plus years ago, and they were talking about the Greeks were trying to figure out the distances to the moon and the distances to the sun. And they came up with a ratio, as I remember, they said 400 to 1, the distance to the moon, distance to the sun, which for, what would you call, back of the scroll calculations wasn't too far off.
Yeah.
Do you know about that story?
I don't know the details of that story, no, but that's definitely part of what the ancient Greeks did that was so fascinating is that they developed geometry. For many people,
Mhm.
geometry was that course you had to get through in high school, but geometry was really an amazing product of the human mind to figure out shapes and angles and distances and how they relate. And once they understood the theorems, the ideas and the formulas of geometry, they were able to do the kind of calculations you described. And they combined geometry with astronomy to begin to get to the first rational descriptions of the sky. Always before, cultures looked at the sky with the gods. The planets were gods,
Mhm.
the sun and the moon were gods, and we were the subject of the will of the gods. But in fact, with the Greeks, we began to figure out the movements of the sky. We began to understand what's up there as natural worlds and not necessarily supernatural gods in the sky. And that was a great step forward for human thinking.
Following up on your comment about the Earth being a sphere, there was some Greek that looked down into a well in Egypt and then calculated the curvature of the Earth. Once again, it wasn't that accurate, but it was amazingly close.
Yes.
Uh, and you should relate that one.
Yeah, well, this is a Greek thinker named Eratosthenes. And Eratosthenes did this remarkable experiment where he saw that on the same day the sun was overhead because you could see it down a well in one city in Egypt, but was not in a well, not overhead in another city. How could you explain he couldn't see it on the same day, but he had reports of the same day, the sun being overhead in one location and off at an angle in another location? How could you explain that? Why wouldn't the sun be exactly overhead everywhere on the flat Earth? And the answer was the Earth wasn't flat, it was round. And furthermore, the angle by which the other city was off from overhead could allow him to calculate using geometry the size, the sphericity, the roundness of the Earth, and therefore the size of the Earth. And actually, Eratosthenes came quite close. He did well in that calculation, much more than that distance calculation. So that you can read about that. That's on the web and in every introductory astronomy textbook. The experiment of
Mhm.
Eratosthenes, measuring the size of the Earth thousands of years ago.
And one
Okay,
other thing I
the
wanted
last
to
one.
mention, but oh, that's another one.
Yeah. The last fun question. If they
Uh-huh.
knew the Earth was a sphere, why wasn't Columbus back in the Greek days?
Yes, yes, that's right. So Columbus actually knew about this, but what Columbus had was the technology to do the experiment, to actually go around, right? Um,
Mhm.
and actually, the at Columbus's day, this was greatly debated. Some of that Greek knowledge had been forgotten in the Middle Ages During the Middle Ages, a lot of Greek knowledge was thought to be dangerous. It was hidden or destroyed. And when the world began to emerge from those dark ages and we tried to recapture Greek knowledge, there was still a great deal of debate about whether the earth was flat or round. And Columbus was one of those, and then later others who looked at really sailing around, trying to figure out just how to get around the earth.
Yeah, one of the things that you mentioned about the Earth and the moon and the sun being of similar size there,
Mhm.
that if you go back to the early experiments on general relativity, that came in very handy during a solar eclipse to show the phenomenon of bending of light rays as they go across the sun, as opposed to where they were when the sun wasn't there. And that's
That's
kind of
right.
an interesting. They wouldn't have been able to have done that experiment so earlier if they didn't have that.
That you're absolutely right. This is I was mentioning to David that I'm teaching now a course for retired people, which I call
Hmm.
Einstein without tears. And I try
Hmm.
to explain Einstein's work without the mathematics. And John, you're quite right that in fact, one of the great initial proofs of Einstein's bizarre general theory of relativity, in which he proposed that gravity could warp space and time in a very profound way. One of the early proofs was that he said, if you look at gravity in the solar system, every world that we're familiar with has pretty weak gravity, and the effect that my theory predicts is unmeasurable. But there's one place in the solar system with enough gravity to measurably warp space, and that's the sun. So if we could see a beam of starlight coming by the sun, we would see its path changed ever so slightly by this warping effect of the sun's gravity. The problem is you can't see beams of sunlight coming by the sun because the sun is so darn bright. But during an eclipse, as John points out, the moon exactly covers the bright disk of the sun. The sky turns from day to night. Starlight is visible near the sun. And so a team of astronomers from England and other countries went to see where that eclipse was visible in 1919. They took a picture of starlight coming by the sun. They went back to England to develop the photo, and the starlight was out of place near the sun by just what Einstein had predicted. And this is what made Einstein famous around the world. That experiment was one of the things that made Einstein a worldwide scientist.
You mentioned in your notes that you sent me about in the past month Vera Rubin Observatory, which we've talked a lot about on the space show, is going to make the greatest movie of all time. It's not yet operational, or it is operational.
It is. In fact, let's talk a little bit about the Vera Rubin
Okay.
Observatory. It's not a space telescope. Uh, it's a telescope on the ground in Chile, but it has the largest and most sophisticated digital camera ever built attached to a telescope, which is a pretty good sized telescope, an 8.5-meter mirror, 8.5 yards wide. And it's going to take a regular picture of the entire sky all the time. And then it will repeat and take a picture of the entire sky, moving around, taking a picture and assembling it. And then it will take another one. And for 10 years, it will take a continuous picture of the sky and then stitch it together into the most sophisticated and most detail rich movie of the sky ever made. So that's why people are calling it the greatest movie of all time. Um, but it's not going to be the kind of movie you can watch with your eyes, but with digital analysis, this 10-year movie is expected to show us millions of new things in astronomy. Undiscovered asteroids coming into the solar system, moving across our field of view, dying stars exploding, and various places in our own galaxy and elsewhere, all kinds of great bursts of energy that we're now observing in many different kinds of waves. All that will become visible to us in this movie. And they just announced last month that it's starting. The movie is starting, and we are beginning the 10-year period. So astronomers can't wait for this movie. Already there will be releases all the time, and there's a host of institutions linked into the telescope that get the data and can work with the discoveries even while the movie is slowly being assembled.
But the movie per se is not visible real time.
No, no, you're absolutely
Yeah.
right. The movie will be stitched together ultimately, but the discovery as it goes through the sky and then compares it to the previous time it went through the sky, all kinds of discoveries will become visible within days. So they're expecting that every year they're going to find thousands of new asteroids, for example. They're going to measure orbits of asteroids we hadn't been able to measure before. They at one point they thought that they would have 10 million alerts per night, that there will be 10 million things that the computer says this changed from the last time. Pay attention to it. Now, no
Mhm.
one can keep up with 10 million alerts. We don't have enough graduate students to do that. So clearly what we're going to need to do is record all this on computers and have AI sift through it, and then astronomers deal with this wealth of data. But we'd much rather have an embarrassment of riches than no riches at all.
Is there a Vera Rubin at home feature like SETI at home?
Yes, there is. And they're still working on the details of that. But there is going to be, uh, for example, there's already a group called the Rubin Comet Catchers, which is going to be looking for new comets in the data. It's going to be a citizen science um, project. So just Google the Vera Rubin Observatory, Rubin, Vera Rubin Observatory, and there's a scientific part to their website and there's a public part to their website, and you can see some of the things that are going to be offered for citizen scientists or amateur astronomers to play with the data.
Fantastic. Is Vera Rubin the only resource doing this kind of thing now, or do we have other telescopes also doing similar things to Vera Rubin?
Oh yes, this is we are living in an era of amazing telescopes. I mean, as you very kindly mentioned, I write an introductory astronomy textbook, which is free on the web, and we have to keep up with all this. And we're really tired as textbook authors because so much is being discovered and so much is changing. We have to continually update the textbook and put new pictures in. So it's both exhausting and wonderful at the same time. And as you point out, the Vera Rubin telescope is on the ground, but we have an amazing, relatively new telescope in space as well. And that's the James Webb Space Telescope. So far, the only telescope named after a government bureaucrat, but we'll forgive them. And the James Webb Telescope is the largest telescope ever put into space, but it's not a telescope for looking at light, like the kind of light that our eyes can see. It's a telescope for looking at what we call heat rays or infrared waves, which tells us more about sort of heat in the universe than light. And adding that information to the Hubble Space Telescope, which tells us what's happening with light, is opening up a whole new window for astronomers. And the James Webb Space Telescope has been up there now for a couple of years, but it's really just starting its work. And because it's much bigger than the Hubble, it can let us look further away. And for astronomers, and this is a fun thing to think about for everybody, looking further away means looking further back in time.
Is
If you
there
haven't heard that before, that's quite a mouthful. But because light only comes to us at a finite speed. The speed of light is very fast, but it's not infinite because light takes a while to get here. Because things in space are so far away, it takes a while for light from astronomical objects to reach us. For example, the nearest star, the nearest sun to us, is 4 light years away. So the news we get from that star is 4 years old because that's how long it took the light to get here. And if we look at other galaxies, other great islands of stars, they're millions or billions of light years away. And so the light from them takes millions of years or billions of years to reach us. Now, if you were raised on CNN, you might say, well, wait, what do I care about billion-year-old light? That's ancient history. But for astronomers, this is not a curse. It's a blessing. Because what do you expect your friendly neighborhood astronomer to do for you? One of the things the public expects of us is to put together the history of the entire universe. How are we going to put together the history of the universe? It's already happened. But by looking at faraway things, we see light from long ago. And the further out we look, the longer ago we're seeing. So the James Webb Space Telescope has enabled us to look back further than any other telescope, to look back almost to the time of the Big Bang, to the origin time. And we are starting to see what structures existed in the universe in those primeval days when the universe was still getting together, gathering structure. And it's fascinating and surprising to see what we can see in those distant places and long ago times.
Is there any realistic way that they can take what they see? For example, on one of my shows, we almost exclusively interview astrophysicists and scientists and astronomers on what they're publishing in Nature and Science. And, they're talking about supernovas and disappearing black holes and all sorts of things. Is there any way to accurately extrapolate or determine what would be happening today if they could see that object in real time rather than a billion years ago?
What a great question. Yes, indeed. Um, can we look at objects near us and say, these are the modern versions of what we're seeing long ago, far away? And the answer is not always. It's a very good question and one that's got a lot of astronomers scratching their heads right now. The things we're seeing with the James Webb Space Telescope at the beginning are things we're not seeing today. So something in that early universe started out differently than we expected. For example, we're seeing the earliest galaxies, the earliest structures of stars, as tiny little red blobs. And some of them already have huge black holes in them way too early. Our theories can't fully explain why these tiny red blobs of forming galaxies have black holes, why they have certain properties they do. How did that early series of structures turn into what we have today? And the connections are not at all clear right now. So I think a generation of graduate students is going to get their PhDs trying to figure out how to connect that distant past to the present we see in our own neighborhood today.
Yeah, I've always wondered if the early expansion of the universe in the earliest instance where things were very dense, that is it possible that quantum fluctuations in that early situation created black holes that then started merging with each other that many of these things actually emerged before the microwave background period that we can observe, and that they come out that way with black holes very early in the universe. I'm wondering about that.
Yeah, you're right on target. This is one of the things people are talking about right now.
Mhm.
That is it possible? Black holes, for those who are not black hole fans, black holes in today's universe are places where really big stars at the end of their lives, when they've run out of fuel and can't support themselves anymore, these giant stars, these massive stars collapse, and no
Hmm.
force we know of in the universe can stop them from collapsing forever. And that's quite a statement. But what happens when a star like that collapses? Well, we go back to what we just talked about a minute ago about Einstein's theory of warping space. As a star collapses, as it gets more and more, I'm going to use a technical term here, squozen, like fresh squozen orange juice, as the star gets collapsider and more squozen, gravity gets greater and greater and greater at its surface until it becomes so dense, so squozen, that light trying to go near it is actually trapped in a circle and can't get out. And if light can't get out, what color will it be? Black. And if light can't get out, nothing else can get out. So it's like a hole. You can throw your teddy bear in, but you can't get it back out. So astronomers call these collapsed dead stars black holes. And we understand pretty well how a star can make a black hole. But what John is asking is, could the beginning of the universe have had space itself so twisted and complicated that it made black holes with the initial matter of the universe much earlier than it made stars? Could black holes have been some of the earliest members or ingredients of the forming universe? And that's one interpretation of these James Webb Space Telescope ideas or observations, is that black holes formed much earlier than astronomers could have anticipated.
And not necessarily due to stars collapsing, but due to the early, very early universe turbulence, if you will.
Yeah, thank you.
Yeah,
Absolutely right. That
yeah.
due to the twisting of space and time in that dense universe that exploded as a Big Bang. That's exactly.
Admittedly, this is one conjecture and it's not established yet.
That,
It's just a concept that
you're
might
not
have some
getting the
validity.
Nobel Prize for this idea quite yet. But it's there to be had. Yes.
Yeah.
Is
Um,
is the ability to take one of these little red dots from the beginning of the universe area. Actually, they're not quite at the beginning, but close enough. And then speed it up to figure out where it is today or what it would be today or what happened to it. Is this strictly a deal of needing more data and computer power so that the AI or the software can just factor in 10 billion different variables and then say, here's scenario one, here's scenario two? Is that what it's a function of? And
I,
then can the AI program extrapolate and generate the data that is needed? And would there be any degree of accuracy to any of this?
wow, that's like three questions in one. Let me see if I can separate those out. So, first of all, to learn more about what these early little red dots are doing, we need even bigger telescopes. If you go to an astronomer and get him drunk and say, what's his greatest wish? It's always to build a bigger telescope, put it in space or whatever it is, make me as big a telescope, a bigger mirror as you can, because I want to see even better and even further out in space and time. So, one answer to your question is we need an even better version of the James Webb Space Telescope to give us more detail. And so, but the other question, the other part of the question is, do we need a better understanding of what John was talking about, what the early universe was like in terms of the ripples of space and time and the theoretical description of what the Big Bang was like? And so, just as much as we need good observations, we also need better theories of how all this works. And we're approaching it from both ends.
No end in sight.
No, this is guaranteed employment for astronomers. The universe just gets mysteriouser and mysteriouser the more we learn about it.
I would like to ask about one of my favorite little history things, and that is the speed of light. And the planet Jupiter, and some guy by the name of Galileo and his first telescope, and
Mm.
making a rough calculation for the speed of light.
It wasn't Galileo, but Galileo discovered the moons. And then it was
Yeah.
another scientist who did the calculation. But you remember quite right that one of the things that human beings are always marveling at was how fast light was. I mean, when you turn on a source of light, you light a candle or you turn on a bulb, you seem to see the light instantly. And people wondered, how fast was it really? And at the time of Galileo in the 1500s or 1600s, there was no way of measuring speeds anywhere near as fast as the speed of light. So people knew it was fast, and that was about it. But Galileo was the first person, or roughly the first person, to use a spyglass, a telescope, on the heavens. And one of the first things he did, turning the telescope to the heavens, is he looked at the planet Jupiter and he discovered that it had 4 big moons going around it. This was the first thing ever discovered that didn't go around the Earth. This is what got Galileo in trouble with the church, because the church decreed that the Earth must be the center of all creation. And why didn't the moons of Jupiter get the memo? Everything's supposed to go around the Earth. What's going on? And indeed, these 4 moons were perfectly happy going around Jupiter. And we eventually understood their orbits and their distances and learned more about them. And one of the things that was interesting to see is that sometimes the moons were in front of Jupiter and sometimes they were behind Jupiter. And when they were behind Jupiter, they were further away, and the light took longer to get to us. But when they were in front of Jupiter, they were closer to us, and the light took less time to get to us. And by watching how they went around, we were able to measure from the difference in front and in the back a rough estimate of the speed of light. So that was the first measurement of the speed of
The,
light
the,
with
the other
Galileo's
point
moon.
the other point that I got from that story was one of the best clocks ever found, I think, was Io, and it's circling around and round, and it's a perfect clock because you could see the eclipse when Io went behind Jupiter, and you could calculate when it was going to be and where Jupiter was around the sun. And all of a sudden, you can start extrapolating with algebra the speed of light.
Yeah. This is Io is the innermost of the
Yeah.
4 moons that Galileo discovered. It's the one that has the fastest orbit around. So that's why you say that it's the best clock in terms of keeping track of things. Yeah.
Andy, speaking of the speed of light, I seem to remember in my history there's an Old West cowboy story of a guy who was a kid who was in school and kind of a weirdo, and he figured out a way to build some kind of a telescope or something to measure the speed of light, and he later became the founder or the head or something with the Naval Observatory. Do you know the story I'm trying to
I'm
remember?
sorry, I don't know that story. That's not one I'm familiar with.
Um, I'll have to look it up, and
Okay.
um, I remember seeing it in one of my old West movies, and then I did look it up, and yeah, the guy was part of the Naval Observatory creation when he grew up. So
All right.
it'd be the
Something
late
for a future
1800s.
show.
Yeah,
This couldn't have to be Michelson or Morley, the two.
I don't know if there's a Wild West part to
it
Michelson
might
and
be
Morley.
Well,
Michelson. I don't remember, but somebody could probably Google it and find out real quick if my memory is faulty or
All
not.
I once saw that in a Western, not in a textbook or a history book.
Okay.
No, but I verified it, and they said it's a true story, and he did go on to be part of or helping to found or do something with the Naval Observatory,
Well,
physics. So if somebody has a minute and wants to try to find it, uh,
maybe that was a youthful person that eventually did this experiment. That I don't know the history, but I did see a Western with that in it once.
So,
Long time. I was like,
well, I'll look it up, and looks like Marshall's trying to find it right now. So,
Mm, I I don't have a keyword to work off of. Um,
Well, let's move
hmm.
on, and we can
speed of
come back.
light in the Old West, and just see.
I'll give it a shot.
But uh, there's no citizen science that I've seen with the James Webb Telescope, or have I missed that possibility?
Well, there's a place that you can go called Zooniverse, Zooniverse, Zooniverse. And Zooniverse is a collection of citizen science projects. And it used to be that there were three or four where you could use data as a rank beginner and make interesting discoveries. But now there are so many Zooniverse projects, it's impossible for mere mortals like me to keep up with it. So that's one place that if you're interested, you can go and see what kind of citizen science projects are available. NASA also has a citizen science page where NASA projects specifically make data available. So if you just Google NASA and citizen science, you should be able to get to a citizen science page just for NASA projects. So there are so many that I can't keep up with them, but that's a good place to go. If you're interested in you take a few lessons, and then you can take the data that these space observatories make available and mine them for interesting new things. And kids in high school have discovered planets around other stars. College students have made all kinds of discoveries. And when you discover something like this, the scientist often puts your name on the same paper as the scientist. So it's really a nice thing to have on your resume that you've been a citizen science discoverer, even as a young person. So it's something that people might want to check out as a possible project for the future. But we're getting a lot of discoveries from that. And I should mention that if you were to ask me what is the biggest change I've seen in astronomy in my career, the biggest change is that when I was a graduate student, we knew zero planets around other stars. The only planets we knew about were the planets orbiting our sun. And we thought that the technology to see a faint planet around a bright star light years away was just not something we could do. And since 1995, we've gotten that technology in several ways, and we now know 6,000 planets orbiting other stars, and more are being discovered almost every day. 6,000 planets are now known going around other stars, a whole bunch of different stars. And so this has been a revolution in astronomy. And we're starting to understand these planets a little bit. Some of them are Earth-like, many are Jupiter-like, some are not like any planet we have in our own solar system. So it's absolutely fascinating. And that's one of the areas where citizen science has been really useful, looking at lots and lots of data from these specialized telescopes and finding new planets with the data.
So, what does this tell you over your career as an astronomer about the likelihood of finding advanced life?
Well,
Not
this is
molecular life, but sentient life.
this is indeed my favorite question in all of astronomy is, are we alone? Could there be spatial listeners on other worlds listening to their version of Dr. Livingston giving wonderful shows about what's out there? And maybe one of the stars they're looking at is our sun. We still don't have a definitive answer to that. But the fact that the planets that we think are the best place to grow intelligent life um, are abundant. The fact that planets are abundant in the nearby universe, and we think in the whole universe, makes us a lot more optimistic about the possibility of other life forms and maybe even other intelligent life forms out there. One of the things that has been the most enjoyable in my career is that I've had the privilege of being on the board of directors of something called the SETI Institute, the Search for Extraterrestrial Intelligence Institute, which is a scientific group devoted to the scientific search for life elsewhere and trying to find evidence of such a life, which we would call a techno signature, a signature of technology. Searching for techno signatures is, I think, the most delightful part of all of astronomy, trying to see whether or not there might be others like us out there. And in fact, starting tomorrow, there's going to be an international symposium on the search for techno signatures. And I'm very fortunate to be able to participate in that. So I'm looking forward to learning more about all kinds of interesting projects that are being undertaken by astronomers around the world to try to see if we can tune in on signals or see evidence of cosmic engineering by advanced civilizations, or get the heat from a big factory up in space from another civilization. All kinds of projects are underway to try to get signs of extraterrestrial intelligence, and I think that's fascinating.
Um, Another thing I've heard from some guests on the space show that I want to bounce off of you are the theories that as you get somewhat closer to a black hole, the speed of light becomes variable and is no longer fixed. So I'm sure you've heard this and about these kinds of theories. What do you think? Can you explain?
Well, I don't think that it's really the speed of light that's affected. The effect is one on space and time. Speed is space divided by time, right? If you say, how fast are you going? I'm going 50 miles per hour. So speed is just the distance you cover divided by the time you take. Einstein's theory predicts that when gravity is strong, not only does space warp, but time also changes. And at first, this was a prediction that even scientists had trouble with. We all grow up thinking of time as a great river, and we are all caught in the current of this great river, flowing from the past through the present into the future. And everybody, no matter how poor or wealthy you are, you're all in the same current. And what Einstein said was, no, not quite. The current is not the same depending on the strength of gravity and also how fast you move. If you move really fast, time can also be a variable. And so as time varies, it would seem like the speed of light is changing, but it's not that the speed of light itself is changing. It's the changes in space and time near a black hole that give you that sense. And yes, if you were to go very close to a black hole, your time would really slow down. And that would mean that the rest of the universe would be on speeded up time compared to you. So think about that for a second. If I could safely, which I can, go to a black hole and take a long journey around it, my time would inch along and I could come back while the rest of the universe has had regular time and I'd be in the future. Because my time moved so slow, the rest of the universe moved at regular time. If I re-emerged from that neighborhood, I would be in the future. And this has fascinated science fiction writers. There's a whole bunch of science fiction novels now and stories that look at this whole question of what would it be like to use a black hole as a time machine. In fact, one of the things you can read about me, perhaps on the website for this show, is that in my retirement, I've started writing science fiction myself. And at first, I had a bulletin board full of rejection slips from all the best science fiction magazines. But now 11 of my stories have been published. So I'm launched as a science fiction writer. And one of the ones I got published is called Slow Time Station. And it's all about this idea of slowing down time by hanging around very close to a black hole. So if I can make a shameless plug, if you go to my website, fraknoi.com, Fraknoi.com, you can read my published science fiction stories on the website. And you can learn more about what happens to time in that slow time station
So
story.
why does time seem to slow down as you approach the black hole?
It does not seem to, it does.
It does.
It does. It's not it's an actual function of how gravity affects time. And as I say, physicists have trouble with this, scientists have trouble with it. And the problem is that the Earth's gravity is so weak that in Einstein's lifetime, there was no experiment we could do on Earth to prove that Einstein's prediction was right. And I think that was something Einstein was a little bit sad about as he got older, that this really interesting prediction was not yet tested with an actual experiment in an Earth laboratory. But 4 years after he died, only 4 years later, a team at Harvard built the most accurate atomic clock ever built. And this experiment, called the Pound-Rebka experiment, done at the physics building at Harvard, compared very accurate clocks at the top of the physics building and in the basement of the physics building at Harvard. And the basement is closer to the center of gravity, so it felt stronger gravity, and it should have slower time. And the tower at the top of the physics building was higher up, so it should have less gravity, so it should have faster time. And indeed, that's what was measured. They were able to measure that time changed depending on gravity by exactly the amount Einstein had predicted. 1959 Pound-Rebka experiment. Somewhere Einstein was smiling.
Marshall?
Also, this phenomenon you're talking about was pretty well illustrated in the movie Interstellar when they went down to this moon that, and then came back and they only had a few hours down there. Another guy had gotten a lot older when they went back up. Leaving aside that the space dynamics of it was completely wrong as far as propulsion, but
You're right. You're right. That movie, that's a great story. That movie was actually originally written by Kip Thorne, a later Nobel Prize winning physicist at Caltech, who, long story, but got involved with Carl Sagan and was kind of jealous that Carl Sagan got a movie and his black holes didn't, even though Kip Thorne, suggested the black holes in Carl Sagan's novel and movie Contact. Carl Sagan called Kip Thorne and said, I need a black hole travel system for my novel that I'm writing. And one of his graduate students came up with it. So Kip Thorne then wrote a script which ultimately got turned into Interstellar. And Interstellar, as you say, has a very poignant plot device in which a dad promises to come back for his daughter, but winds up near a black hole in slower time and winds up in the future and only gets back just in time before his daughter dies to keep his promise. So that's a very lovely illustration of just what we've been talking about the slowing of time near a black hole.
Marshall?
Yeah, I'd like to go back to David's thing about time getting a little fuzzy around black holes. You also have to consider the fact that there's probably a lot of gases in the accretion disks, chunks of stuff, et cetera, et cetera. So if you're, within half a light year or so on like that, you could be going around the black hole, and yes, you would see gravity becoming denser and less dense back and forth, not because Einstein was wrong, but because you've got so much material between you and the center of the black hole that's in orbit going around, which means gravity is fluctuating.
Well, now let's tell everybody what you're talking about. So a black hole by itself is completely black, And the typical black hole zone where you get trapped is about 20 to 40 miles across for a star that makes a black hole. So what do you have? You have a black zone where light can't get out, 20 to 40 miles across, light years away in the blackness of space. Good luck finding such a black hole. Never will astronomers ever find black holes that are like that. But luckily, nature has been cooperative. And many stars, including some that make black holes, live not by themselves like the sun does, but in pairs or triplets. This was illustrated in the movie Star Wars, where Tatooine, that planet where Luke Skywalker grows up, had two suns in the sky because it was two suns going around each other. When there are two suns in a system, two stars, and one becomes a black hole, the gravity of the black hole can pull material off the living star, and that goes into a whirlpool of accelerating material dying to fall into the black hole. And that's what Marshall's talking about. That's an accretion disk. To accrete means to gather in. So we call these whirlpools of material being gathered into the black hole an accretion disk. And in the accretion disk near a black hole, it's a very complicated situation because you have all this material rubbing against each other and starting to glow with the heat of friction.
Oh, yeah.
And it can be seen even though the black hole itself is completely invisible. So the way we find black holes is not by seeing the black little area, but by seeing this incredibly energetic whirlpool of doomed material doing its best to commit suicide inside the black hole. And that glow is what tells us a lot about the presence of black holes out there.
Hey, Marshall, I didn't understand what you meant when you said that gravity was varying in an accretion disk. Can you clarify what you meant?
Well, as gases and rocks and so on like that come in, it's going to make the gravity vary just a little bit because
Gravity can't vary. I don't understand what you mean.
No, but the amount that a particular particle would feel would depend on the local arrangement of mass.
Oh,
So
okay,
in
I
the
gotcha.
accretion disk, so the black hole gravity won't vary, but the material in the accretion disk can be a substantial amount of stuff. And so for any given particle in that accretion disk, as it swirls from one place to another, it might feel slightly different gravity. Is that
Got it.
what you
Yeah.
meant, Mark? I
Okay.
think that's good.
And I'd also like to throw in, as the star is having material pulled off of it, it's not going to be smooth because the star is going to have solar flares and other phenomena that's going to just make it chaotic.
Chaotic, right? Absolutely. And so, nothing is as simple as the pictures in our elementary textbooks seem to make it be. Things in the real universe are always more complicated. But still, it's
That's
so
why
much
we
fun to
made
think about both the science and the science fiction of these weird places out there.
For the
That's why we invented mathematics, right?
for the students who may be catching our program or watching it on YouTube or something, in today's modern world, with all the tools that are available, what is the relevant difference in going for an astronomy career, a cosmology studies program, or astrophysics?
Wow. Well, so all of those are really astronomy. Astronomy is sort of the overview name. But today, you don't really study what in the Greek days was called astronomy, which was mostly about the description of what we can see in the sky. Today, to study astronomy, you have to study a lot of physics to know how things work inside stars and inside planets and when black holes interact. All of that requires a study of physics, which is sort of the basic principles of the physics world. So all astronomy today is astrophysics. It was Neil deGrasse Tyson who made that term popular because instead of calling himself an astronomer, he called himself an astrophysicist. And suddenly that seemed like a really important title. But all astronomers are astrophysicists.
Is there a
The other
difference?
question is about cosmology. Now, cosmology is a branch of astronomy, a branch of astrophysics, which asks questions about the universe as a whole. I mean WHOLE, not HOLE. The universe as a whole in its entirety. Cosmology is the study of the universe as one system. It is the largest, most pretentious, most overpowering branch of astronomy where we ask what are the properties of the universe? How did it start? How does it evolve as a single system? And what is its destiny? What is its future fate? And that's an amazing branch. So very few astrophysicists become cosmologists, but those who do deal with the universe in its entirety.
So does it matter if your university has a department of astronomy or the degree goes toward astrophysics or
It
none of
doesn't.
that
All
matter?
everybody understands that that's the same thing today. So some people get an astronomy and physics degree because they have a department of astronomy and physics, but those words don't matter in terms of your credentials. So um, it's fine. Uh, if you don't like physics or mathematics, you're unlikely to be happy as an astronomer because you have to study an enormous amount of physics and mathematics to become an astronomer. Uh, but most astronomers, live on physics and mathematics. They love it, and that enables them to deal with complicated theories and observations around those theories, which is what modern astronomy is about.
Since you've been talking about sci-fi, there was a really terrific Netflix series that I enjoyed. I actually went out and bought the three-volume, multi-hundred-page book on the three-body planet problem. Did you see from the Chinese author?
Mm.
Um, and I loved it that the civilization would advance so far and then it would implode and start all over again when the everything aligned differently. And that it's going to take the aliens 450 years to get to Earth, that they've discovered it because of something that SETI talks about is do we really want to have active or passive SETI? What are your thoughts? Did you see it? Are you familiar with the story
Um,
and some
I'm
of
a
those
big
theories?
science fiction fan, so I read the first book, um, and I watched a little bit of the TV show too. I had a lot of trouble with that book, but probably not for important reasons. I didn't like how he switched from this beautiful description at the beginning of the book of the Maoist era in Chinese history, and it was such a lovely,
Yeah, it was
heartrending description of it. And then toward the end, he rushed, and everything was the characters were barely defined, and it was really poorly written. So I just had, as a writer, I had trouble with that book. Also, there are lots of science errors in the description, and there's intelligent particles and things like that, which I have a lot of trouble with. But your question is a more general one, which is about one of the things that we're deliberating a lot about is whether we should do METI instead of SETI. METI is messaging extraterrestrial intelligence. SETI is searching for extraterrestrial intelligence. So in SETI, we sit here on Earth, we tune our telescopes out into the sky, and we see if there's any evidence of them. Maybe messages they're sending to a base of theirs somewhere that happens to be in the same direction as we are, or some result of their technology. But they're not aware that we're trying to find them. Our search is completely passive. If we tune in on a signal, they don't know that we've tuned in. Just like when you tune into a radio station in your car, the radio station doesn't know if you've tuned in or not. So it's perfectly safe to do SETI. But some people are talking about let's get a really loud signal and send it from Earth to announce that we're here. We're intelligent. We're here. Hello. And other scientists, including me, are a little bit worried about that. And the reason we're worried, and please don't take this wrong, is because we think we're the youngest, dumbest civilization in the galaxy. Now you might say, well, how can you say that? But here's what we mean. We only got the technology to do SETI or METI about 50 to 100 years ago. The galaxy is 13 billion years old. In those 13 billion years, civilizations could have arisen 1 million years ago, 1 billion years ago. We only got good enough to be considered a civilization in the galaxy terms less than a century ago. So we're the baby of the galaxy. That doesn't mean there's anything wrong with us. If you go to a cocktail party and someone brings a baby, you don't try to discuss astrophysics with the baby. You just say, goo goo gaga, maybe someday the baby will grow up to be Einstein, right? Or David Livingstone, somebody really important. But you don't try to talk to the baby and you don't expect much from the baby. In the same way, it's no insult to say, just by the fact that we began so recently, we're the baby of the civilization, of the galaxy, of all civilizations. And therefore, we don't know who's out there and whether they're nice or unpleasant, whether there are huge wars going on, if there are terrible civilizations out there that find every new civilization to be a competition they want to stamp out. We know nothing. So it's perfectly okay to search, but maybe a baby shouldn't be so in a hurry to send out a loud message announcing we're here. That's METI. And so this debate is something we're going to have quite a bit of in years to come, because if we eventually do get a signal from an alien civilization, the question will immediately arise, now that we know they're there, do we send them a message? And who decides that? That's the question that Carl Sagan framed as, who speaks for Earth? Who makes a decision about whether we reveal ourselves? Should scientists in some project in Canada make that decision, or the United States? Or is that something the UN should vote on, that we reveal ourselves as a species in the galaxy? Sounds like a pretty important humanity-wide decision. Who's going to make that decision, and how do we get to it? And that's, I think, going to be one of the most interesting questions of the 21st century.
Aren't we broadcasting anyway with TV, radar?
No, I'm glad you brought that up, because that turns out to be very weak. Yes, if they had some incredibly advanced devices, maybe they could tune in on the hum of military radar from Earth. But our TV and radio is really weak. You know that if you live in Seattle, your signal doesn't make it to San Francisco. San Francisco has to have all the TV stations all over again, just like Seattle does, because the Seattle stations are too weak to reach antennas in San Francisco. And every major city has an ABC, a CBS, an NBC, because our signals are pretty weak. So we're not worried that our TV or radio is getting out to hundreds of light years and alerting people. But if we were to send a directed, much stronger message to a specific star, we do have the technology to make that loud enough to be heard. And the question is, should we, and who decides?
Well, our missions have plaques for whoever finds them on our interstellar mission. So in that sense, we're broadcasting.
That's right. Now, we've sent out several spacecraft that are leaving the gravitational pull of the sun, spacecraft called Pioneer and Voyager and New Horizons, and each of them have a physical message in the spacecraft. But those spacecrafts are not going to get anywhere for millions of years. So we'll be a much older child in the galaxy by then. And they're tiny little physical craft, so the chances of them being found, even if they enter a system with a civilization, they'll be so tiny in the vastness of those planetary orbits, not so clear they're going to be found. So I don't think that represents anywhere near the kind of danger that a message that we broadcast specifically in the direction of a known civilization might represent.
Uh, for everyone listening, we're about 15 minutes out from ending the program, but I know you're involved in skeptical science, and I'd like you to share with us your rules or your structure for a BS detector with science or projects.
Well, this is you're absolutely right. Long ago, not long ago now, a couple of decades ago, scientists got really fed up with the gullible treatment of what we call pseudoscience or fiction science in the media. That was especially true in the 60s and 70s, where all kinds of really weird stories, paranormal stories, and ghosts and astrology and UFOs were everywhere in the mainstream media. And so it wasn't just scientists, but magicians got upset because some people were doing magic tricks and claiming they had supernatural powers when they were just doing ordinary magician tricks. So magicians got upset and lawyers got upset. So a group of us who were upset formed a group which is now called the Committee for Skeptical Inquiry, CSI, which a TV show also has the initials of. But the Committee for Skeptical Inquiry, which publishes a magazine called the Skeptical Inquirer, has spent the last 4 or 5 decades publishing what you might call debunking stories, uh, articles, studies that show that the world is a lot more rational than the ghost lovers would want to have you believe, and that we can test a lot of these phenomena that are claimed, and we can see if their claims are real or not. And so far, there's very little that shows any evidence of a paranormal or supernatural world out there that science can't explore. But often it's really helpful for the media to have another perspective before they publish a claim like that. And so that's one thing that the Committee for Skeptical Inquiry has really done is to help media people when they're confronted by a story like this. For example, recently there's been all this talk of pilots taking movies that show UFOs doing weird things in the sky, moving in ways that no aircraft could possibly move. Um, and we have those movies. They're shown on 60 Minutes and other legitimate places. And investigators have looked at those movies. They figured out exactly what happened. They're out of focus cameras. They're looking at things at a very different distance than they thought. So the motion wasn't what they thought. There's a wonderful investigator named Mick West, Mickwest. Google him. Mick West has looked at all these UFO claims and has been able to debunk any that have actual data associated with them. We've found all kinds of things masquerading as UFOs, which are perfectly natural phenomena, including, it turns out, the oily bellies of birds. Some birds landed in an oil slick and their bellies became very reflective. And then they flew over Lubbock, Texas, and those reflective bellies really reflected a lot of light. And that was taken to be a swarm of UFOs, but it was just the oily bellies of birds. If you knew about the oil slick and you knew what happened, you could say exactly how those lights were explained. There are rational explanations for many of these claims. And that's certainly been something that in my teaching and in my writing, I've been trying to emphasize.
So, how does your work and the work of others with this organization, I almost hate to ask you this, deal with faith, like a faith in an afterlife?
Oh, I think faith is not a scientific subject. I don't think there's any problem reconciling faith and science. Uh, in faith, you don't ask for experiments like you do in science. In faith, you have a deep held personal belief. And that's perfectly okay. There are many scientists who have a faith in God and so on, but still do scientific experiments. So I think that's perfectly okay to reconcile. I think if you're claiming that miracles are happening right now in a bodega in Mexico, there you have to go and do the tests. But if you're just saying that I have a deep personal faith in something, it's like love, right? You can explain love in a lot of ways, but there's parts of love that are just beyond scientific explanation, and they don't need to have a scientific explanation. Same way with faith. I don't see any real problem with deep personal faith and science.
But wouldn't your deep personal faith mean you might believe in something that scientifically is not plausible?
Right. I think that then it's no longer faith. Faith is about things that can't be tested. I think
And you
that's,
just accept that and move on.
yeah, if it can't be tested, it's not in the scientific realm. And none of my business as a scientist.
So does that mean it's not plausible in faith, or you just believe it
I
and go
I
on?
don't think that you need to make a value judgment. It's a personal thing. For many people, faith sustains them and helps them through life, and that that's not none of the business of scientists, as long as they don't make a scientific claim, an experimental claim.
Have we omitted something or forgotten something, or this is a good time to go back and patch up the conversation for that which is missing, and the
Well,
same for the others in the room.
I would like to say a little bit about my textbook project because I think it might be of interest to your listeners more generally than just space. So this is a project from at Rice University called OpenStax, OpenStax, all one word. And this is a project supported by many foundations, major foundations, to try to make free textbooks for every introductory course taught in college. If you have relatives in college, you know that college has become very expensive for young people, especially from difficult circumstances. And part of it is that textbooks can now cost $100 or $200 for an introductory class. And the aim of this project is to create online free textbooks for every introductory course. And two astronomers and I were very honored to be asked to write the astronomy textbook for OpenStax. It's all online. You see a blue hardcover printed copy of it, but you don't need a hardcover printed copy, the one behind me. But it's just online. Just go to OpenStax on the web. And there are introductory textbooks in economics, in psychology, in physics, in math, astronomy, psychology, etc. So if you're in college or if you're thinking about teaching yourself some subject, it's a really nice thing to check out. I don't have any financial investment because the book is free. My royalties are exactly zero. So this is not a commercial plug, but many people are really happy to learn that there are these introductory textbooks freely available on the web. And if you're interested in astronomy and space because of this show, I will modestly recommend you might want to check out Astronomy by OpenStax, where we've tried to set out astronomy the way we do in this nice discussion without a lot of math in everyday terms, explaining some of the historical stories that John and Marshall brought in and just giving an introduction to astronomy. So that's my plug for today is check out the free textbook.
Any comments from Marshall, John, or John before we get ready to sign
Yeah,
off?
I have something. Andrew, I met you through Project Astro quite a while ago.
Ah,
But
okay.
I'm also a big fan of the Silicon Valley Lecture Series through Foothill College and the Smithwick Theater. And can you give us an update on where we're at on when those are coming back, or are
Ah,
they still going?
how nice of you to mention that. So until I retired, I taught at Foothill College that you kindly mentioned in Silicon Valley. And we have a giant theater at Foothill College called the Smithwick Theater, which can seat 950 people. And I had this idea, why don't we use that? They use it for musicals and all kinds of other stuff. why don't we use it to have astronomy lectures? And we called it the Silicon Valley Astronomy Lectures. And 27 years ago, we began to use this theater to bring astronomers to give non-technical lectures on what's the latest in astronomy. And it was in Silicon Valley, and suddenly a donor appeared at my door and said, these lectures are so good, you should tape them. I want to give you some money to tape these lectures professionally and put them on YouTube. And I said, well, if you insist, yes, you can give us money to the college. And we've been doing that ever since for 27 years. We've been having these lectures, and for about half of those years, maybe a little more now, we've been taping them in professional style with the slides edited in. And they're on YouTube. Just if you go to YouTube, just go to Silicon Valley Astronomy Lectures. We went to Zoom only lectures during COVID, but we kept going with them. And now we're back in person. So, in fact, we're going to have one March 11th on taking pictures of planets around other stars. But you can find them all on YouTube. And also, my son, who's a much younger and media savvy person than I am, said, Dad, you can't just have it be on YouTube. You need to have an audio version. Everybody's now into podcasts. You should make it into podcasts. And I said, no, who's going to want to listen to a lecture with slides on just a podcast? But it turns out they're very popular, and we've now put them up on podcasts. And we have 4 million views on YouTube, and we already have 250,000 views on all the podcast services or downloads, I guess you call them. So thank you for asking. They're still ongoing, 6 a year. Just Google Silicon Valley Astronomy Lectures. That's very kind of you to ask.
Any other comments from any of the people in the Zoom room with us?
No,
Marshall,
I'm good.
John, anything from you?
We're okay.
All right, until the next big celestial event, okay? Let me know,
All right.
and we'll reconvene. And thank you very much for being here. Do you still do those short radio clips on Bay Area radio stations on astronomy?
Well, the radio station is in most towns. There are very far fewer talk shows now than there used to be. That's why podcasts are so popular. So
Uh-huh.
in the Bay Area, we used to have KGO
Right.
radio, which was a talk show station, and it's been discontinued. And there's really only one talk show left in the entire San Francisco Bay Area. Well, no, there's also PFA, KPFA, but only KQED radio has talk shows. So I don't get to do as many talk shows now, but I get to do podcasts like this or Zoom shows like this. And I still try very much to keep up with astronomy and to share the excitement of it with as many people.
What is your podcast called so we can find your podcast?
It's called the Silicon Valley Astronomy Lectures.
Okay.
Silicon Valley
All
Astronomy.
right. Listeners, remember I'm off next week as I'm at UCLA, and we come back and look for your joining us then, and follow the newsletters to see who's our guest going to be. Thank you very much, Andrew. I appreciate it. And Marshall, John, and John, thank you as well. Everybody have a great weekend. Go see the eclipse. And again, that is going to be early in the morning on the 3rd of March, West Coast time, correct?
Right. And in each time zone, it'll be early in the morning, before dawn on Tuesday morning, March 3rd. And
Okay.
thank you for having me.
Thank you. Everybody have a great rest of the weekend. And as we like to say, keep looking up. And goodbye from Andrew, John, Marshall, John, and myself.